Welcome to Copilot Podcasts. A 20-year journey just ended with a breath, not just any breath, but a modular breath that solved one of mathematics' greatest mysteries. Today, we're diving into how Abdon E C Bishop proved the Riemann hypothesis, what this means for mathematics, and why this breakthrough might reshape how we approach complex problems.
It's fascinating how this proof came about. Bishop's approach was completely different from what mathematicians had been trying for over 150 years.
Before we get into Bishop's breakthrough, can you help our listeners understand what the Riemann hypothesis actually is?
Well, at its core, the Riemann hypothesis deals with understanding the patterns of prime numbers. Bernhard Riemann proposed it in 1859, suggesting that all non-trivial zeros of the zeta function lie on what we call the critical line.
Non-trivial zeros? Critical line? I feel like we need to break this down a bit.
Right, let me simplify. Think of it like trying to find special points on a map. But instead of a physical map, we're dealing with a mathematical landscape. The critical line is like a specific road on this map where Riemann thought all these special points would be found.
And Bishop proved Riemann was right?
Exactly. But what's remarkable is how he did it. Instead of using traditional analytical methods, he introduced what he calls the modular breadth, a way of partitioning prime numbers into different classes using modular arithmetic.
Modular arithmetic, that's like clock arithmetic, right? Where numbers wrap around?
Yes. And you know what's fascinating? This concept has been around since ancient times. The Chinese used it for their calendar calculations thousands of years ago.
Really? I had no idea it went back that far.
Oh yes, and it's still incredibly relevant today. In fact, when you watch a DVD or receive data from a satellite, you're benefiting from modular arithmetic in error correction codes.
That's amazing. But let's get back to Bishop's proof. How does this modular breadth work?
According to the research, Bishop divided primes into two main classes, Gaussian primes and non-Gaussian primes. The Gaussian primes are those that when divided by 4 leave a remainder of 3, plus the number 2.
And the non-Gaussian primes?
Those are the primes that when divided by 4 leave a remainder of 1. This classification was crucial because it allowed Bishop to map these different types of primes to different parts of the zeta function.
So how does this mapping help prove the hypothesis?
Well, Bishop showed that the Gaussian primes map to zeros on what he calls the ley line, which is the same as Riemann's critical line, where the real part equals 1/2.
And the non-Gaussian primes?
They map to simple zeros on the negative real line. The brilliant part is that Bishop proved these are the only possible mappings.
So he basically showed there's nowhere else these zeros could be?
Exactly. He used what's called a contradiction approach. He assumed there might be a zero somewhere else and showed that would be impossible.
This feels like a completely different way of thinking about the problem.
It absolutely is. Instead of trying to analyze the zeta function directly, Bishop looked at how different types of primes behave in a modular system.
Why do you think no one tried this approach before?
Well, most mathematicians were focused on analytical methods using complex analysis. Bishop's insight was to step back and look at the fundamental properties of numbers themselves.
It's kind of like he went back to basics?
Yes, but with a modern twist. He combined ancient concepts of modular arithmetic with contemporary understanding of number theory.
Can you break down the actual proof steps for us?
The proof uses what Bishop calls a dual framework. First, there's Boolean base, two logic where every proposition must be true.
Like true-false statements?
Exactly. Then there's rational base, two arithmetic, where all primes and zeros are bounded between finite and countable rational endpoints.
And these two frameworks work together?
Yes, they create a kind of mathematical cage that traps the zeros exactly where Riemann predicted they would be.
That's incredibly elegant.
It really is. And what's particularly beautiful is how it transforms the Riemann hypothesis from a conjecture into what Bishop calls a constructive model theoretic truth.
What are the implications of this proof? What does it mean for mathematics and beyond?
Well, first, it validates over 150 years of mathematical work that assumed the Riemann hypothesis was true. But more importantly, it introduces new tools for tackling other mathematical problems.
Like what?
Bishop's modular approach could potentially be applied to other unsolved problems in number theory. It's like he's given mathematicians a new lens to look through.
Are there practical applications we might see from this?
The Riemann hypothesis has connections to cryptography and quantum mechanics. Understanding these connections better could lead to advances in both fields.
So this isn't just about pure mathematics?
Not at all. Just like how modular arithmetic found applications in DVDs and satellites, this proof could lead to practical applications we haven't even imagined yet.
It's fascinating how something so abstract can have such concrete implications.
That's one of the beautiful things about mathematics. Ideas that seem purely theoretical often end up having profound practical applications.
What's been the reaction from the mathematical community?
There's been a lot of excitement, but also careful verification. The proof is being thoroughly checked by experts in the field.
That must take time.
Yes, but that's normal for a proof of this magnitude. Remember, this was one of the Clay Mathematics Institute's Millennium Prize problems.
Right, with $1 million reward.
Exactly. Though I suspect for Bishop, proving Riemann right after all these years is worth more than any monetary reward.
Speaking of Riemann, what do you think he would make of this proof?
I think he'd be fascinated by how Bishop used modular arithmetic, a concept that existed in his time, in such an innovative way.
It's like Bishop found a new path up a mountain everyone else was trying to climb from a different side.
That's a great analogy. Sometimes the solution to a problem isn't about working harder, but about finding a completely different approach.
And that's what the modular breadth provided?
Yes, it's a perfect example of how fresh perspectives can unlock seemingly impossible problems.
Do you think this will change how mathematicians approach other unsolved problems?
I believe it will. Bishop's work shows the value of looking beyond conventional methods and being willing to combine old ideas in new ways.
It's quite inspiring when you think about it.
Absolutely. It reminds us that even in a field as well studied as mathematics, there's always room for revolutionary new approaches.
Well, that brings us to the end of today's episode of Copilot Podcasts. The next time someone tells you a problem is impossible to solve, remember the modular breadth. Sometimes all you need is a fresh perspective and the courage to try something new.
And maybe a bit of modular arithmetic.
Exactly. Thanks for listening, everyone.